This is a projectiles or SUVAT question. Part 1 is a simple one-dimensional SUVAT problem. Part 2, we're resolving to work out different components of velocity as our golf ball is launched at an angle. For parts 3 and 4, we're calculating time of flight and vertical distance travelled. And finally, for parts 5 and 6, we're discussing an alternative path for the golf ball to make it land with a smaller horizontal velocity. Figure 3 shows a golf ball at rest on a horizontal surface 1.3 meters from a hole. A golfer hits the ball so that it moves horizontally with an initial velocity of 1.8 meters per second. The ball experiences a constant deceleration of 1.2 meters per second squared, and we want to calculate the velocity of the ball when it reaches the edge of the hole. In this question, we have constant deceleration. If we have a constant acceleration or deceleration, we can use SUVAT. So let's write out a SUVAT table. So we have the displacement is 1.3 meters. The initial velocity is 1.8. We're trying to work out the final velocity, and the acceleration would be minus 1.2 as it is a deceleration. And with these four quantities, we can use v squared is equal to u squared plus 2as. So v is then equal to the square root of u squared plus 2 times a times s. And this gives us 0.3464. All of our numbers in the question are given to 2 sig figs, so then I'll give the final answer to 2 sig figs as well, so 0.35 meters per second. Later the golf ball lands in a sandpit. The golfer hits the ball, giving it an initial velocity of u at 35 degrees to the horizontal, which we're given on our diagram. The horizontal component of velocity is 8.8. And we're trying to work out the vertical component of velocity. We're trying to show that this is 6 meters per second. So for this, we can draw a velocity triangle. So this is u. This angle here is 35 degrees. And we're told the horizontal component of velocity is 8.8. We're trying to work out the vertical component. Relative to the angle 35 degrees, we want to work out the opposite, and we have the adjacent, so we can use tan. Tan of 35 is equal to opposite over adjacent, rearrange, so it'll be 8.8 tan 35, which will be 6.162 meters per second, and that's approximately 6. For 3.3 we have, the ball is travelling horizontally as it reaches point X. We have the same initial velocity as before, u at an angle of 35 degrees to the horizontal. We're assuming that weight is the only force acting on the ball, so no air resistance. And we want to work out the time for the ball to travel to X. So if weight is the only force acting, that means it's the resultant force. There will be a downwards acceleration of 9.81. So we can use SUVAT again. There's no acceleration in the horizontal direction. We're assuming air resistance to be 0. Whenever you have these kinds of two-dimensional projectiles questions, I'd always recommend drawing out a table, a SUVAT table, for the vertical and the horizontal components separately. And then once you have that, you can then think about what equations we can use to work out whatever we need to find. So let's do that to start with. Okay, so we have the initial horizontal and vertical components of velocity. From the previous question, the vertical component of velocity was 6.162, and the horizontal is 8.8. Vertically, the acceleration will be minus 9.81. I'm setting the upwards direction to be positive, so acceleration is therefore negative. We're trying to work out time to travel to point X, and the key thing about point X is that when the ball reaches this point, it is traveling horizontally. So that means that there will be no vertical velocity at point X. If it's traveling completely horizontally, the vertical velocity is 0. So in our SUVAT table, our final vertical velocity would be 0. And then from these four quantities here, we can then work out time. We can use v is equal to u plus at, t is equal to v minus u over a, which is then 0 minus 6.162, all divided by minus 9.81, and that gives 0.63 seconds. And to more decimal places, I'll put it in the table, that would be 0.6281. .4 is related to 3.3. We're using the same suvac quantities. We want to now work out the vertical distance of x above the initial position of the ball. So we can use the same suvac table because we are considering the same start point and end point. We're still considering going to point x over here. So then our suvac table remains the same, and now we are trying to work out what the vertical distance of the ball would be at point x, so this quantity here. And we can use any equation that involves s to work that out. I'll use v squared is equal to u squared plus 2as. S is then v squared minus u squared over 2a, which is 0 minus 6.162 squared all over 2 times minus 9.81. And that gives me 1.935 to 2 sig figs, 1.9. So I'll deal with the final two parts of this question together. So we have the golfer returns the ball to its original position in the sandpit. He wants the ball to land at x, but this time with a smaller horizontal velocity than before. So same start point, same end point, but now we want to have, when the ball lands at point x, we want to have a smaller horizontal velocity. We're trying to figure out what a trajectory for this ball would look like, and we want to explain the reason for selecting this trajectory. Okay, so let's start by thinking about this intuitively. If we have a golf ball and we want it to land at the same point as before, but now with a smaller horizontal velocity, so remember that before, the golfer hit the golf ball so that it lands at x with only horizontal velocity, so it's traveling horizontally when it lands at x. We want the ball to have less horizontal velocity but land at the same point. So one way we can do that, if we think about this intuitively, is if we hit the ball more upwards, so give it a greater vertical velocity, so that it follows this kind of trajectory, and then it comes down as it's going to land at point x, that will be a trajectory which will have a smaller horizontal velocity. So that's an intuitive explanation for the trajectory that we will have. Let's try and talk about this now in terms of equations. So if we think about, first of all, consider the horizontal direction. The only equation that we can use in the horizontal direction is speed is equal to distance over time. So our horizontal speed is equal to the horizontal distance divided by time. And the horizontal distance is unchanged. So the distance from here to point x, that does not change. We still want the ball to land in the same spot. So if we want our horizontal velocity to decrease, then we will want our time taken, time of flight, to increase. And if we want our time of flight to increase, the only way that we can do this is if we were to increase the vertical component of velocity. So let's just recap that. Horizontal distance stays the same. In order to decrease horizontal velocity, that would mean the time taken, the time of flight, must increase. For the time of flight to increase, the vertical component of velocity must increase. If you increase the vertical component of velocity and you decrease the horizontal component of velocity, that will basically look something like this. Before, the velocity may have been this, and afterwards it will be something like this. Blue arrow has a greater vertical component, lower horizontal component than purple arrow. Okay, so then our trajectory would look like this, something like that. And now for our explanation,